multiple times during the season that different apples come in at different times. The Cortland apples, right? At least one. Okay, so today we'll take up one topic. If you're designing a study and had your choice, would you do a paired study or not have a paired study, matched pair study? And then some introduction to analysis of variance. Right? And so analysis of variance is really covered initially in the chapters 5 and 6. And so some things on contrasts are talked about some in chapter 5, and some formulas are given in chapter 6. So in kind of reading through this and studying that, it makes sense to go through 5 first, but I think it would be helpful to look at the topics as they're spread out over 5 and 6. And if you notice contrasts and tests and standard errors and assumptions talked about one place and then they're kind of talked about again, so they kind of go together. The book has this logic for splitting things up. Mostly I'll stay to that, but some things might get a little more attention from 6 when they come up, because it seems more natural to do a little bit more with that. Right? So here you go then. Okay. Right, so paired versus paired, not paired, right? Matched pairs. So if you wanted to think about this off the top of your head, should I use pairing? Right, in a study. So there's a few things that you might think about. What do you think we should look at? What do you think would be important in thinking about designing a study?
The samples are independent.
Can you get independent samples? Right. Kind of a time one, like a pre-test, 2 different time periods. Can you get 2 independent samples? Can you do pairing? Right. So can you get independent samples? Right. So there's one of the examples about birds on islands, right? And then at one point and at another point, well, if they only have a lifespan that's so long, you're not going to do pairing. Maybe you could tag one group of animals, but if you can't find them again, you can't really measure them. So sometimes it's not possible, and you really have to think about 2 independent samples. For other things that you're interested in, maybe it really is, you think that individual change is going to be the dominant factor, right? Sometimes the pairing gets rid of some confounding bias. Is confounding an issue for 2 independent samples? So one's really at one time, like the bike lanes, how many accidents they have at one time period, and a couple of years later, looking at those. Well, if there's kind of couldn't use randomization, then there becomes a kind of a challenge of taking 2 independent samples, and there's just going to be a change. And so these kind of gets, feasibility. How challenging is it to go back and do another interview with the same people? Maybe just too burdensome, depending on what they're going to do, or costly. There's a feasibility issue. Maybe there's some bias that you'd be concerned with by not using pairing. So those kind of things get done. We could also look at variability. And so other things being equal, you probably want to do the procedure that gives you more accuracy. And so we could look at that a little bit. Right? So in the paired study, we could get in pairs. But if we had the same two independent samples, right, we maybe could have two in cases, in per group, in pairs, right, two measurements per pair. So we're getting two in measurements. Maybe there's some cost savings actually. Sometimes we're getting the same households with the same people involved. The current population survey and most studies of unemployment or poverty take the same people at different time periods, because once you've gotten all the demographics and background information and learned about the family structure and so on, you don't need to repeat necessarily all those questions, or they can go much faster the second time. And also, once people have agreed to do this study, they might be more likely to do it again, right? But let's say we're doing a confidence interval for the difference between two means. Right? Either way we do it, whether it's this would be kind of the change. So we could be taking the differences here or independent measurements here. We could still be interested in that change, right? And in this case, we're going to, for the pairs, we're going to take the difference between two measurements, right, and then report d bar. Right? And over here, we're going to have, y bar 2 and y bar 1 for the two independent groups, and then look at, the difference between these two things. Back to line. And so numerically, the d bar and these, if the measurements have the same sizes and everything, right? So you could end up with these two things being an equal value, whether they're paired or not paired. And could end up being the case, right? And so then the question is, how accurate is it when you do the pairing or you take two independent samples, right? And so we've looked at t-test procedures for both of those things, right? So if we're doing confidence intervals, based on d bar, the margin of error, MOE then is margin of error. We would take a t value, and with pairs, right, there's n pairs, we could use n minus 1, and then we're going to take this s sub d over the square root of n. If it's two samples, right, we have y bar 2 minus y bar 1 as the difference. If we have, let's see, two values here, if we have like a pooled one, well, I'm just going to write it like this, and we'll talk about that. So we would do S1 squared over the first sample size, and then S2 squared over the second sample size, and take the square root of all that thing. And if sigma 1 equals 6 sigma 2, we'd use a t distribution with 2n minus 2 degrees of freedom. Right? So a little space between those two. And so our margin of error would have a different t value here and a slightly different, right, a value there. Right? And so what is, these things might be the same, so eventually we'll pool them. Right? We'll make some assumptions about that shortly, right? But what is the standard deviation of the difference? Right? Well, each of these di is a y, is the difference of two values. The variance of a difference is like the variance of the measurement, right, plus the variance of the second one, minus 2 times a covariance. Right, this S12 is the covariance of those, because they're not independent measurements. The pairing means there's a non-trivial covariance. And in most of our applications, we'd be considering this, we're going to have a positive covariance, right? So we're adding these two variances together, but we're subtracting twice the covariance. Right? So this S sub d, if there's a large covariance, might go down. So we have a difference in degrees of freedom in here, and we have this thing that might be going down. One different way to write this covariance, the covariance can be calculated as the first standard deviation times the second standard deviation times a correlation, where R is a correlation between these things. So these standard deviations are here, and the thing that's different in this equation is this, besides that formula, is that covariance, right? You can kind of think about a covariance, right? So we're going to make some assumptions about these magnitudes. Right? Let's assume, just for, so we can do a comparison, that S1 and S2 are 1, right? Close to 1, right? Equal and about 1. Then this is 1 plus 1 minus 2 times, well, let's write that on the next page. Right? To make this concrete, let's assume that these are equal, and we'll set them equal to 1. That's really kind of arbitrary. You could have some other multiplier there, sigma, multiplying everything, and it would just kind of cancel out. It would be a constant on all of those. So the margin of error, the S of d, right, then is 1 plus 1, that's S of 1 squared, this is S of 2 squared, minus 2 times the covariance. So S of 1, 2 was S1, S2 times R, but if they're both 1, this is just the correlation. So this is 2 times 1 minus the correlation. And so then our margin of error for the paired side is our t, which used n minus 1, 0.975 percentile. And then S sub d is 2 times 1 minus r. We divide that by n, and it's square root of that whole thing. Before we wrote it as S sub d, which is the square root of that. Right? On the right side, for the match study, right, we had the t with 2n minus 2 degrees of freedom, and we had S of 1 squared over n plus S of 2 squared over n. Right? But if both of these things are 1, right, then this thing is going to be 2 over n, right? 1 over n plus 2 over n. So we're going to have a 2 over n here, right, as the kind of the half width of the confidence interval, the margin of error. Right? And we want to choose the option where that's smaller. Right? And it's going to depend on the R, right? What correlation we actually have between the measurements. And those sample size can function into. The sample size affects its degrees of freedom. Right? So R is between -1 and 1. So the 2 times 1 minus r over n, that square root, assume r is positive. That's a parenthesis there. So that part is less than or equal to 2 over n. Right? So the pairing, as long as there's some correlation, makes that one smaller. Right? But it's better to have more degrees of freedom. Right? This number, the 2n minus 2 cut off, is smaller than that one. Right? So there's no clear winner. Right? The t n minus 1 cutoff, 0.975 cutoff, is going to be bigger than the t 2n minus 2, the 0.975 cutoff. So this would make the left side bigger, but the correlations make that one smaller. So it's how correlated it is and the kind of the impact on sample size. Right? As sample size gets big, you get sample size in the thousands, there is very little difference between these two numbers, even though it looks like that, right? But if n is 5 or 10 or something, then this number is quite a bit smaller. Smaller. You're going from 2.02, 2.2 down to 2.0 or something like that. So he's making a little difference here, but it's all about the correlation. So if we put these two things equal, we can figure out where is it a tie. So 2n minus 1, and then this thing was 2, 1 minus r over n square root, and it equals t of 2n minus 2. So where is it a tie? For margin of error. And this one was just 2 over n square root under these assumptions. So the square root of 2 over n cancels, right? And we get t n minus 1, and there's a square root of 1 minus the correlation here equals 2n minus 2 on this side. So if we 1 minus r, if you put the 2, this t n minus 1 over here, and square everything, right? So you can put this one underneath, divide by both sides, and square it, and then we can express this in terms of the correlation we would need, right? So it'll be 1 minus this thing. So that's where they're equal. If the correlation equals this t ratio, then it's equal margin of error. But if r is bigger, this size, if it gets closer to 1, this size gets smaller, and so the margin of error will be smaller. So r is bigger, then paired has smaller margin of error, and it's better. And have I done this all right? I think I've solved that correctly, right? So the top up here is less than the bottom, right? This is a smaller number, so this is less than 1, and you're squaring it, so it's still less than 1. So 1 minus that, so something less than 1. And so the question then is, how big does correlation actually have to be for that to work out? So if you do it, say, so the quantile for t is 0.975. If n is, we need 2 times, say we had 10 per group, pretty small sample size, times 10 minus 2, that's the independent sample one. And if it's 10 minus 1 for the other one, that ratio about 93%. Right? But we square it, and it comes out to about 0.86. But we're taking 1 minus that in the formula. And so we get about 0.14. So, if I've done everything right, that's where the r is equal. That's where it equals that number. So if r is bigger than that, then we should get a smaller margin of error for pairing. Which means that a correlation of 0.14 is not too high. So we could really benefit from this pairing even if the correlation is pretty modest. If I haven't So pairing very often gives you a benefit, right, if you can do it. Right? It could require more effort to go back to the same people, to find two people that are similar and match them up before the study. That could be a big issue. It might just easier to get one group of patients and another group of patients as they come into a hospital, and the actual process of pairing them up could be quite hard to do. So there could be a lot of feasibility issues of doing it, but we can use, part of the point of this is that, taking the margin of error formulas, the confidence interval formulas that we've done in different cases, sometimes with a little bit of assumption and a little bit of, equating, you can come up with something more analytical that kind of guides some things in study design. Another reason for doing this is kind of reviews those two, the contrast between the paired and the two independent samples in terms of degrees of freedom and margin of error formula, standard error formula, and things like that. So, but any questions about the derivation? So I just took those two formulas, the two margin of error formulas, put them equal together, made an assumption about the standard deviations. I had to work through a little bit of what that covariance was to figure out how to equate it, but then you can get something. Not overly complicated to do. So where you can encourage people to do studies with matching, if it makes sense. And there's going to be a positive correlation. It often can be really good to do. But in many studies, the feasibility of matching, like taking students and tracking them to their previous test scores, if you can't store ID numbers or personal information in any way, it becomes pretty hard to do the matching. Right? So, well, that's kind of one topic I've been thinking. I think that's an interesting question to think about, how to do those things. The next topic we really want to move on to is multiple samples. But are there any other questions about comparing one sample or two samples that we've done? Right, so in this chapter 5 and 6 is analysis of variance. So one way analysis of variance. Abbreviated ANOVA. And so in this scenario, we have two or more groups. And let's say that the groups be indexed by I, capital I groups. And then there's individuals within groups. And they can be indexed by J. And let's say there's n sub I individuals in that jth group. N sub I individuals in the ith group. Right? And so the total sample size is going to be a sum over the different groups of the different sample sizes. So little n sample size is the number spread across these groups. Right? And people don't switch groups. We assume that the groups are well defined, and people, some people work in the issues where people switch groups on you, or you for a while. There's some designs where you expose people to one treatment for a while, and they cross over and then get the other treatment, and you randomize which treatment goes first. So there's other designs where people switch groups, but in this case, we're not going to do that. We're going to assume that the groups are independent of one another. And we also assume that the individuals are independent of one another. And so you can have, so randomized controlled trials. People come in with a certain condition, like prediabetes, and the diabetes prevention program, the randomized controlled trial. People come in with prediabetes, they have elevated blood sugar, elevated weight, maybe some other risk factors, but not fully clinically diagnosed as diabetic yet. And then they're consent and are randomized either to a placebo pill, metformin pill, or a lifestyle coaching. And then the individuals, the lifestyle, they have individual personalized coaching, and this they're giving a pill. The placebo pill is made to look like the metformin pill and have some of the little same similar taste, right? So that can't really tell them apart. And people are randomized, and most of the people are not in families or a couple. They might see each other in a clinic and things like that, but there's not that much interaction. There's a little bit of this, but mostly it's pretty close to that independence, right? And so you can have 3 or more things in a randomized trial. Sometimes in education or psychology, people are naturally in groups, so children are taught in classrooms. And so you might worry about this individual, about this. You might just, which sample size is more important, the group sample size or the individual sample size, right? We can look at, there'll be a trade-off in terms of which one do you want to really maximize. Do you want to do more classrooms, or do you want more students within classrooms? Psychology, if there's counseling and there's group counseling, or there's, in economics for, work training programs, if it's done in a group, right, then some of this independence assumption of individuals might be a little bit questionable, a little bit harder to get done, right? So you could, we're going to measure things in every group, right? So Yij is going to be group I and person J in that group. So the I's go 1, 2, up to our number of groups, and then the J's go 1, 2, up to our sample sizes in those groups. And we want to know, on average, are the groups different? Our average responses by group. Different. So we can do some graphical things. Right? It's always good to look at your data. So graphical. Side-by-side box plots. For these things, or histograms by group. It's good to put the histograms on the same scale for all of them. Right, some groups might be a tiny scale, and others might be doing it on their individual scale, allowing them to vary. Might be better for looking at normality, right, to see if the data look roughly normal, or if there's particular outliers for those groups. If you have a group that's really narrow but the overall range is very big, that one histogram can get kind of mushed together. But if you let it spread out, you're looking at it both ways, right? You get two different focuses. One compares group, and one studies within that group a little bit better. Right? And then there's different summary statistics that we can do. Graphical and basic summary statistics for comparing groups. We'll put that on the next page. But if you're writing an article summarizing the result of an experiment, you probably do show some graphs. That's easy for people to take away, and very illustrative of the data. But then you might have a table also that gives averages, standard deviations, sample size, and things like that. Right? So what are some of these summary statistics? So we have, right? Well, the sample mean in group I. Group I is 1 over n sub I. individuals, your sample mean in that group. J. Right. So certainly you can compare those. A useful comparison is the overall mean. We had n was the overall sample size, and so if you add up all the observations, I'm going to just leave off the limits there. But this would be a sum over all groups and all individuals. This is equivalent to taking the sample size times each y bar I in there. Right, so there's an overall average. And some of our analysis of variance testing, in a way, will be comparing these group averages to where the overall is. How far is that away? So we could look at some deviations, group deviations. Y bar I minus y bar. Right. Some of those will be positive, some of those will be negative, right? And so we're kind of looking for the magnitudes. Which ones are small? Are there any of these group average differences that are pretty big? Right? But we're also going to look at just general variability, right? We would have within the groups, group I will have the sample variance, SI squared, right? We can divide by the one less than the sample size in that group and just take the yij minus y bar I squared sample variance in that group. That's really going to be an important measure of the spread within that group, and we have the spread across all these. At some point we're going to make an assumption about variances for the standard F test, that the variances are equal. So you can look at the graphs. Do the spreads appear quite similar? Does this variance appear equal? Right there. And if it is equal, we're going to pool them together. Right? We're going to combine all the measurements of a variance into a composite so that it's a stronger, better estimate of variance. And that becomes one of the key features of analysis of variance. Right? Is that because we get a pooled variance estimate, we get to get more precise inference across a whole wide range of tests and things like that. It's going to benefit us through a whole lot of things through chapters 5 and chapter 6. So the pooled one, S of P or S, right, is where we can take the deviations, right, of the individuals within their group, yij minus y bar I squared. So when it's written like that, it means take the sum of squared deviations for all those in group I, and then add those deviations together across all the groups, and we're going to divide by n minus I, actually, there as a pooled version. I'm going to write sample variance up here. I just rewriting this word up here so I have a little more space to fit the next bit in there. Right? There's a different way of writing this, right? This thing is the numerator of this. Right? So if we multiply each of these SI squared by this one less than the sample size, it's going to give us just that little component there. Right? So another way of writing this, right, we can do n sub I minus 1 SI squared, okay, over there. And another way of writing this, well, if we add up all the sample sizes, that's the sum of the n's, right? And there's I groups, right? So if we subtract 1 from each one, we get that. So this can be written as I and y minus 1. So there's a couple ways of writing that pooled variance estimate, right? Kind of an averaged, in a way, estimate of the individual variances. The weights, the way that they're weighted together is by degrees of freedom, one less than sample size. So, are the means the same? So there'd be a population mean, mu1, mu2, etc. Are these all the same or not? So we have hypothesis. A null hypothesis would say that these several means are all the same. No difference. So if you had, the multiple medical testing, is there any effect going on in the study in terms of the average differences? If there's, different reading programs and ways of teaching reading at a certain grade level, and you've collected data from many different school systems, and they do slightly different variations. Some do some variation on phonics, some do a 50-50 mix, some do more, traditional, some have more of a hearing, listening, I don't know. So they could have a whole variety of things. And the null hypothesis would say there's no difference in any of those. So the alternative then becomes some mu sub I does not equal mu sub I prime for some I and I prime not equal to each other, right? So there's some difference out there. At least one of the means is different from another mean. They could all be different from each other. There could just be one that's standing out as different, but there's just some difference out there. Right? So before jumping to getting a statistic, we can think about kind of an overall summary test statistic. We can look at think about some of our sample data. How's it going to look different? Right? So under H0, what would we suspect under H0? The key statistics, right, are these I's, right? Null hypothesis is true. Right? We're going to expect them to be pretty close together. Right? So we expect y bar I close together, and we expect them to be near to the overall y bar. Right? They won't all be y bar, right? The overall mean, but they'll be, relatively speaking, sample size, adjusting for the sample size and variability we have, they should be kind of close to that, right? So we can measure that distance y bar I minus y bar. Okay. Some of those are going to be negative, some are going to be positive. They actually average out to 0 right, across those if you go through the algebra. So we calculate something called sum of squares, SF, sum of squares. For the groups, if we're comparing groups, is we're going to take the y bar I minus y bars and square them, make them all positive and squared, and then add that up over all the groups. And we're going to weight it by the sample size. So that'll be one measure. Called sum of squares groups. Right? So the farther away you are from that overall y bar, right, the bigger that's going to go. And if there's a fairly sizable group that's farther away, it gets a pretty big multiplier. Right? There. But this thing is going to grow with sample size. Right? Take a bigger study, this thing's going to get bigger. Right? It's kind of hard to judge. It's kind of relative size. So what could we do? Well, we could divide by something, right? We can divide by something. So the MS is going to be a mean square, or kind of an average square, right? So mean square groups is taken to be the sum of squares groups, right, divided by I minus 1. It kind of adjusts for the number of groups. It doesn't fully adjust for the sample size, what was the little int of I there. But it's a kind of a first scale adjustment. If you had more groups, this thing would continue to get big, and that kind of makes kind of an average per group. Right? We still want to know, is this thing, this mean square, is that large, right? Is it, we have, for I groups, is this kind of average spread? Well, we can look at, compare this to spread just of data values within groups. That there's some natural variability. And you can, if it's random, and there's really no difference, then the points are clumped together in different groups. So how spread out the y bar i's tend to be is influenced by how just variable the data are, right, and the sample size. If they're really big sample sizes and the null hypothesis is true, you'd expect the y by i's to be very close. Right? But if it's small sample sizes, the y by i's might just fall further away because there's more variability within the group. So there has to be some aspect of variability within the group. Right? So within groups, we want to account for within group variability. And so we need to judge, we need to be able to judge if the sum of squares groups and then the mean square groups associated with that, right, is large. Is it larger than chance would say it should be under the null hypothesis? And so sum of squares error, sum squares for error, well, we're going to take each yij and subtract its average for its group and square those, and we're going to add them up. So I is going to go from 1 up to I, and j is going to go up from 1 to n sub I. And that's a letter J there. So within a group, it compares its measurement to its average. And there's some, we square them so that they're all positive, and add all those up. We're going to add up all those deviations across that. Right? But again, that's going to grow with the sample sizes and all that. So mean square error is that sum of squares error divided by n minus I. Right? This is that same as this S squared pool that we talked about as a measurement of kind of the overall variability. So ultimately we're going to compare this mean square error to our F statistic is going to be called some mean square for groups over mean square for error. Right? And this is our test statistic. So the null hypothesis is true, and in this mean square groups, the y bar i's are all close to y bar. At least they're pretty close in comparison to what's kind of the natural variability in the system. Right? Then that f is going to be small. On the other hand, if some of the y bars are far apart, right, then this numerator is going to get big. Because the sum of squares error is computed within groups, it doesn't matter that the groups are different. Right? You can have very different groups, averages, but if all the points are focused around there, it doesn't blow up the sum of squares error, but at very different group averages can make the mean squares, the sum of squares groups go really big, right? So if it's large, we're going to reject the null hypothesis, but to evaluate the test statistics, we need its sampling distribution, or its null distribution. So we have a model. Right? For this, the model says that Yij has a group mean plus some random error. And the Eij's are going to be distributed as a normal distribution with some variance. And they're independent of one another. right, is one way of writing that model. Right? So that the response Y we see is the true mean plus some random noise, some random deviation. In probability theory, this can be combined with Yij. You might write it given mu sub I is distributed as a normal, centered at its mean with that variance. Right? So this model says each group is normally distributed around its own mean, and the variances are kind of the same. So pictures that would come out of this ideal model. Right? So you could have, one normal here, another normal over here, and then something else over here. So maybe this is groups 1, 2, and 3. So these are the distributions for the Yij's. So maybe you have two groups that are a little bit different, one that's a little bit higher. And so the values you see, right? If you see a group from this, that's from that group, and then some green ones, here's a sample of points coming from this group, and this one, this one over here will have a sample of points, and it's certainly very plausible that it would overlap with the red one there. And so we would compute, y bar for call that the first group, and then something like y bar for the second group over here, and then a y bar for the third group based on the sample. And so our data would kind of line up like that, right? This would be a case where the null hypothesis is not true, and there's really some differences. And we think that those differences probably might show up. Right? If, however, the means are all the same, so under a null hypothesis that mu1 equals mu2 equals mu3, then right, you really only have one curve. Right? You only have one probability density that says where these values are. Right? And now if you get data, that sample could be there. This sample is probably going to be somewhere, kind of around like that. It's hard for me to draw it as random. I tend to kind of put a couple outliers here, something like that. And so then the averages for these different groups kind of end up being really close. This one's over here, something like that, right? So the three averages ended up being here, and they overlap. And so we want to be able to test between this scenario and a scenario like that, right? And you could have these two could be exactly the same, and one could be different. And once you get 4, 5, 12 groups, whatever, you get all different kinds of patterns. Right? And so it turns out that under a null hypothesis, if the means for the several groups are true, if H0 is true, then the F statistic, which is the mean square for the groups over mean squares error, has an F probability distribution and an F distribution, it's a ratio of two random variables, so it has 2 degrees of freedom. This one is I minus 1. Remember, there are I groups, so it's 1 less than the total number there. And the mean square error had n minus I. Right? The total sample size minus that, or the n sub I minus 1 right there. And so if the null hypothesis F is skewed, right? And so we'll reject the null hypothesis, right, if F is large. Right? And so if the F is greater than our F distribution, if it's kind of 95th percentile. Right? So if we get an F statistic that's up here, this is our rejection range. And we use 95% up here and 5% up here. And so it's a one-sided test in that sense. everything's squared, so all the deviations, whether they're negative or positive, become positive, so it's all folded over on that side. So that's the basic setup, and we'll do more with contrasts and testing. You know, once you decide that there is a difference, you want to find out where the difference is. Is it one group that's different, or all three different, and so on. And do interesting things like that. But any questions? Let's look at a data example, and then certainly if you have different questions as we go on, we'll, on Wednesday and Friday, talking about different issues with this, right? We can talk about those. The two data sets that are in this chapter 5, one has, it's two different diet, or several different, 6 different diet schemes, and some lifetime measurement in there, numerical measurement. The second one has 7 different judges. One judge was of interest because the makeup of the juries or the venues, where in terms of males and females, what percentages they were having in different trials. Right, so there's different groups. One's more of a randomized experiment, one more is an observational study. The diets, let's see now, I'll attach those two things, have them loaded in here. The diets, there are 1, 2, 3, 4, 5, 6 different diets considered. The judges there's this one that's kind of interest, and then some comparison ones. You find similar people, similar jurisdictions, similar types of trials, and so on for comparison. Here's a graphical comparison of the diets. Try it again. Do any of these diets look different than the others? This kind of looks like a couple are kind of lower than this other group. So not only do we want to confirm, testing that there is a difference, which it looks like there's going to be, but then we're going to go on and say which ones are different and how much different. There's also some outliers, so equal variances, normality, maybe you want to think about that. Here's the ones for percents of, I think, male-female representation, and Spock, this last one over here, is particularly low, particularly different than those. But, that one's a little bit different, but there's quite a bit of variability. So is it going to end up being significantly different, given that there's, quite a bit of heterogeneity? I think so, but, we can look at that. The basic analysis of variance command in R is done with this linear model. So LM is a linear model. And that's it, you have an L and an M. And so we get a Y variable as a function of something else. This lifetime is a function of diet, this little tilde, right? And I've already attached the data set, so I don't need to tell it what data to use. It figures that out, right? But LM provides some output, a linear model. So we just do that part of it. It's not quite as useful. Right, so it just gives some coefficients. That's not as useful to look at. But the ANOVA then puts it into a better presentation, and this is what it gives. It gives a little table, and we haven't written all this out. But the diets define the groups here. There were 6 of them, so it's giving I minus 1. It's giving sum of squares and mean square related to the groups in here. The residuals, instead of error, call this residuals. There were, this must be n minus I, so I was 6, so 349 different individuals. There's a sum of squares error, or sum of squares residual, and a mean square. And so we're comparing these two things, and we get this enormous F value. F values under the null hypothesis are going to be near 1. So this is 57, so that's enormous. There is a pretty big difference in these diets. That's there. We'll go over the ANOVA table and exactly what the entries are, but I'll just show you a little bit more. So there's an AOV is a different command for analysis of variance. In there it gives the same output. It's kind of two different implementations. The ANOVA command and the AOV or summary in R as technical things are actually these lists that have a bunch of different things. Right? Just like the t-test command actually is a list of different components. And it gives you a little display of it, which you can use. But for some of the things we might want to do with simulation, we might pull off little pieces of it. Right? So it actually has, you know, a degrees of freedom, sum of squares, p-value. There's a p-value, mean square. So pulling out different things. Here's what the ANOVA table looks in like the judge case. It's also highly statistically significant. There were 7 judges, so 6 degrees of freedom. I think 46 total, the number of rows of that case, 0502. There's 46 judges total, or measurements total. So that minus the 7 judges is that one. The sum of squares for the treatment, sum of squares for the groups, sum of squares for judges in this case in particular. And then it's mean square. And then if you do residuals or errors, it was this and there's that one. And the ratio is about 6.7. So again, it's very, very small. Right? So the quantiles for an F distribution, right? If we want the 0.95 cutoff value, how big would that F statistic need to be? In this case, when it's 6 and 39 degrees of freedom, it's 2.34. So we would be able to reject the null hypothesis if F is over 2.34, but we actually got 6, so we're well beyond that. It's like when we did the simulations of the sampling distributions, then our value was completely off the scale, right? For the election one, right? It was just so far off, it was very significant. So there is a big difference between these things. Right? Here is one other example. I can't exactly remember where I found this. I think I was just looking online. There's a data file here about personality types. Okay. I think if you go to this personality project, it'll give you a description, but it's kind of neat. You can get it off the web. There's something called the Personality Project. Web pages go back and stuff, academic study of personality. And in there they had something on analysis of variance as an example with a data set. And so it gave some nice code for getting the data there. These, so require putting it in there. It had a little bit different, slightly different variation in code, but there was something about dosages of drugs. So table, did I attach it? Okay. Attach data sample 1 in their world there. There were 3 different dosage levels, A, B, and C, pretty small sample size. Box plot, what are the names on that thing? Names. Let's just look at the whole data set. This little dosage and alertness is the Y variable. I'm not going to give too much context of this. If you do a box plot of alertness versus dosage, well, again, it looks pretty clear that there's going to be a difference. But it's small sample sizes. So, you know, we're going to do a pooled thing of variance, so that our estimate of variance might be kind of in between these things. So, and then if you do the analysis of variance on this thing, you get degrees of freedom, sum of squares, mean squares, and F. And again, it's a significant result. So we'll kind of go back over the ANOVA table and the testing a little bit more. But then we're going to look at some of the issues. Is the model really appropriate? Right. This one, are those equal variances? What impact does it make? that doesn't have them? And what might you do instead of that test? So. All right. See you on Wednesday. And some work here on Friday. This is a handout. This is a handout for Friday. You weren't gone on Friday.
Thank you.
Uh-huh.